All right. Am I audible?
Yes, sir.
Yes.
Yes. Okay. Okay. Let's begin now. Okay. Is my screen visible?
Yes.
Yes.
All right. So week 4 is about actually it starts the main point about week 4 is value iteration and asynchronous dynamic programming, uh, and then we move on to Monte Carlo methods. So before week 4, what we have been covering is what Sir has been covering is the uh, the main topic which was covered in week 3 was policy iteration. So policy iteration, uh, it has two steps. One is policy evaluation, and the next one is policy improvement. So this policy evaluation is actually a iterative approach to update the value function for each state, and once when we perform this iteration, this policy evaluation, it will involve multiple iterations until we converge within a certain error, uh, within a certain quantity, which tends to be very, very small. And when we do that, we stop policy evaluation, and then we move on to policy improvement, which is just a greedy step, greedy with respect to the value function learned in previous step. We keep doing this as long as it takes to stabilize the policy. And when we say that, that means the policy does not change, and then we assume that it is stabilized. So this is one policy iteration, and we continue this multiple times to make sure that we reach to the optimal policy. Okay, so now we start from this. Now we look at another approach to uh, reach to the optimal value function and optimal policy, and that is actually value iteration.
There's some result about this, right? Like if we are greedy, then we can always reach an optimal policy or something.
Right, right. That is generalized policy iteration.
Okay.
Right. So we'll talk about that. Uh, so policy iteration is one version of generalized policy iteration. There's another version which is value iteration, which we are going to look at right now. So both of these stand at the extreme spectrum, extreme ends of the spectrum of generalized policy iteration. We'll talk about that.
Actually, can we clarify what is the meaning of an optimal policy? Because in some cases, like in the grid world example in some of the lectures, it's seen that you want to move from some position to the goal position. Then multiple paths are optimal. That's what professor said, right?
Right,
But
right.
one path had a lesser cost, or rather a lesser reward. And the other path, it had a greater reward, and the other path had a lesser reward. Uh, does that mean that optimality doesn't depend on reward as such?
No, actually, it does depend upon the reward. And if I don't recall that particular example. I definitely remember sir showing some 2D grid in which we start from the left bottom position going to the right top. Is that
Correct, correct.
that the one
That's
you're
what I
talking
mean. And he was drawing some random routes through it. But it's like, let's say, like in that particular example, we can say that L1 distance is the cost, which means negative of that would be the reward.
Right. So, so
If
the
you
setting was
minimize the L1 distance, you should get the optimal policy. But he was drawing multiple lines and he was saying that all of these are optimal policies.
okay. I'll have to look at that example, but what I can assure you is, see, if there are if you follow multiple policies and they result in different value functions for the start value, starting position, then all of them cannot be optimal.
All of them cannot be optimal.
Right. So one of them has to be suboptimal, the one which is giving you lesser expected reward from the starting state.
Okay, okay. I thought optimality simply depends on whether the game is solvable or something like that, but it means that lesser reward is suboptimal.
Yeah, definitely. Lesser reward is suboptimal. So if the setting, if I remember correctly, was something like this. So every step you take is -1, and if you reach the goal state, the reward is 0.
Yeah.
Something like that, right?
Yeah, yeah.
Yeah. So I'm pretty sure this is the this should be the case that optimal policy should give you the most reward.
Most reward.
Right. So if I recall correctly, this is how the this is how the optimal policy is defined. So V or I should say not V pi, but V star S is equal to max of all pi's over all pi's E underscore pi of S
For all S, I think.
for all S in S, right?
I see. So that maximum is what is optimal.
Right. Maximum is what is optimal.
Okay. And V pi will be a scalar, right? It will be some real number.
V pi will be
Of S.
yes, yes. It will be scalar numbers, right?
Okay.
So
And
now
what do we call that? We call that the optimal reward, is it? Or value function, as in, okay, it's expected long-term reward of starting from a state. So yeah, it's a scalar.
so if we start from V pi S is how we can define is from state S. What is the expected reward if we follow
If we
policy
follow
pi? V star S means from all the policy space, we take the pi, we take the policy which gives us the maximum value function, maximum reward, and that's our optimal value function.
Okay.
Okay, so value iteration does not start over here. So value iteration, the equation looks something like this. Pk plus 1 of S equal to maximum of I'm going to just write the equation first and then we'll talk about it. My R plus gamma of V A of X. Right. So we're going to talk about a lot of things. This equation is going to give us, kind of a starting point for many things. prime comma r. So see what this equation is doing is okay. So think about this one particular this portion which is highlighted in blue. So what do you think this means?
I think it's the average of reward starting from the next state, is it? S prime?
No, starting from S. So okay. So if you remove this for a second, if you don't consider max of A and we multiply it by okay. So maybe I should copy paste this one and write it this way. Sum of I S given A right. So what is this this equation, the equation on the top? It's just one step of policy evaluation. Does it make sense?
So sum over A, which means all of the actions that we have. What is
Right.
S given A?
S given A is the probability of transition. Okay. So with policy pi, you in state S you take action A and then you move to S prime.
So should that not be proper pi of S prime given A?
Sorry.
The first term, the first sum, should it not be pi of S prime given A?
Oh, sorry. Actually, I wrote it incorrectly. It should be A comma S. Yeah, like this.
So S is got it. Yeah, S is the starting point because S cannot be the result of something. You're already at S.
Right.
Okay. So what are all the actions I can take at state S? Sum over them something.
Right.
And what is it that I'm summing over? It's clearly the mean of something because there's probability multiplied by something else.
Right. So okay. So if you remove the sum for a second, just assume that it is it's a deterministic.
It's only one action.
Right. Then it is in state S what action you take with policy pi. Okay.
Yeah.
With that policy, you so even if you ignore P for some for a few seconds, which is transition which tells you the transition probability as well as the reward distribution. So that says that from state S, you have taken action A, you've gone to state S prime, you received reward R, and what was the previous iterations, previous steps S prime's estimated value function?
Previous or next?
See, it is Vk, and we are computing Vk plus 1. So from previous state value estimates, we are computing next iteration of value function.
So yeah, that's actually exactly makes sense. It's the expected return of playing a policy pi. Acting according to a policy pi.
Right. So this is k plus 1 step estimation of value function for state S.
But the last term, that is V sub k of S prime. S prime is so S prime is a result of. No, S prime is just a variable. It's not really anything.
Right. So Vk S prime is the value estimate for state S prime in previous iteration.
Yeah.
Okay. So it's so this is completely synchronous. What it means is initially all the state values are all the value function for all the states are initialized with 0. Okay. Then we compute V1 with all the V0s for all the states. Then we compute V2 with all the V1 of the previous states. Does it make sense?
I see. So V0 of S is 0 for all S.
Yes, that is true.
And accordingly, okay, we have to fix some gamma, some R because my, okay, P will be obtained from the MDP table, right?
Yeah, P is transition probability from MDP.
RSA, that whole thing will come from the table. Gamma will be given.
Gamma will be given.
It will have to be less than or between 0 and 1.
Yeah, it sits between 0 and 1.
Okay, so it's recursive.
Yes, it's recursive, and that's why we can
That's
use.
what I mean by synchronous, which means you can't get to V2 before you have V1.
Correct.
Okay.
So, since it is recursive, we can use dynamic programming, and that's what we are doing, right? So we have turned dynamic programming expression of Bellman equation into updatable. Make sense?
Yes, and but how do we know how many steps we have? Okay, we have that threshold. So if Vk plus 1 minus Vk is a small number, we stop.
That is right. Right. So yeah, right. So that's what sir also sir explained in the video lecture, that before you update the value function for a state, you create a copy of it, and after you update, you take the difference before and after update, and if it is for all the state, if it is very small value, some theta, then you say that you can stop your algorithm and you are ready to move on to next step, which is policy improvement.
Can you explain that part a bit? Make a copy of what? Because it will be just one number, right?
Okay,
so you can always have a previous and a current.
Right. So for value, okay, this is also it's not value iteration. I'll move it here.
Okay.
It's fine. So what we do is, let's say
V1 equal to subfunction of
yeah. So what we do is, let's say P is some temporary variable, and this is V of S. So this is the previous iteration's value, right? Of the status. Then we apply this formula, and what we do is we compute, right? We compute the difference between these two quantities, VKS plus 1 okay, and this should be smaller than some small number, which is
epsilon or something.
Epsilon or theta. So if this statement is true for all the states, okay, then we say that okay, policy evaluation is done. We are very close to our value functions for the current policy. Then we can move on to policy improvement. Make sense?
So okay, so when this particular stage is reached, we can use the value of either Vk plus 1 of S or Vk of S as the actual value.
Actually, it is Vk plus 1 only, because we don't update it after that. Once you compute it and you're sure that value function for all state is within some small number, the updates are not changing by much. That means you have converged, you don't have to change anything.
Okay. So like if we were writing a function for this, where then the return value of that function will be Vk plus 1. Like what it's giving us, this whole exercise.
Yes.
Exercise, what it's giving us is Vk plus 1.
That is true.
Okay, fine.
Okay, so this is
or V star S. Is that what we can call it?
V star we cannot call it, because to reach the V star we have to improve our policy.
Right. No, you're right. This is because pi here is fixed. We are not doing anything changing on pi, right?
Right. So this is policy evaluation. Once this policy evaluation is done, we can move on to policy improvement, which is selecting the pi prime. So it will be pi prime of S equal to argmax for A Q S comma A right. So one more thing. Score. Okay, so this is how we'll get phi prime, which is the uh, policy. Once you have updated the value function for all states, you get the then you go do the greedy step, which is this one. You take the action which is going to give you the maximum reward starting from that state.
But why can't we simply do policy evaluation for every policy? And that
Policy
will give
value.
me the best for the value of the best value function for a given policy.
See,
Right?
this is that the best value function for a given policy, and that policy doesn't have to be optimal, right?
Correct. So I just do, let's say I have 3 policies. I just run this recursive thing thrice,
Mhm.
each time for a different pi. Whichever
Okay.
returns the highest number is the best policy.
That is true among the three. What about the other policy in the policy space?
Oh, and policy space is infinite or like
For deterministic policy and deterministic MDPs, I don't think it's going to be infinite, but very, very large. But
it will okay. So it's not you cannot iterate through it through the policy space.
sorry.
We cannot iterate through the policy space.
Yeah. We don't want to do that. That's going to policy. The policy search is going to be expensive. We don't want to do that. So instead of doing that, we have this policy iteration where we, start with some policy. It could be random also. Then do the policy evaluation, find out the value function. From that, we start with the policy improvement. So we take one step towards the improving our policy towards the optimal policy and optimal value function.
Okay. I think this is what we mean by policy has to be sampled. It's not something that is given like a discrete realized set of numbers.
See, policy doesn't
Because
have
it
to
will
be.
contain probabilities, so that is why. I mean,
Okay.
especially a stochastic policy will contain probabilities, right?
That is true. A stochastic policy will contain probabilities. However, it doesn't have to be sampled. I mean, in particular state. So when you define a policy, what it means is in certain state, what action do you prefer, or what action will you take with with what probabilities? So if it is a stochastic probability, then there are multiple actions with some probabilities attached. If it is deterministic probability, then it will only have one action in
Got it.
each state.
So only if it is deterministic, or if my is it possible to have one deterministic and other non-deterministic policies? Yes, it is, right?
It is possible.
Which again is why you cannot enumerate each policy specifically.
Okay, that's something.
Given an MDP, we cannot say how many policies are there.
See, if we are talking about stochastic policy, yes, the state space is very, very large. It's going to be blown up. I think it. I have to. Yeah, it can be infinite. That is true.
Okay.
If it is a stochastic policy we are talking about in finite MDP, but if we are talking about deterministic policy in finite MDP, then we are pretty sure it's going to be that set is not going to be infinite.
Right, but still large enough that we cannot do that brute force kind of thing where just take one policy, maximize it.
Right. So
and
see,
then take another and maximize and take the max of the max kind of.
Right. See, so in order that we avoid that brute force approach of finding the optimal policy, we have this order of partial ordering of policies, right? So if I have another policy which gives me a slightly better result in any of the state than my previous policy, the new policy is actually better. I can start from there. I don't have to worry about anything else.
Yeah.
Okay. So this is our policy evaluation, policy improvement algorithm. Now here you will see that now we are going towards value iterations. Value iteration is a form of generalized policy improvement iteration. Sorry. So here, think about this. What we are actually doing. We are first making sure that our value function converges with respect to policy pi. Then we do the policy improvement. Then we go, if there are no improvement, then we can say that this is the optimal policy. But if there is any change in the pi prime, then we go back and do the policy evaluation again. Then go to policy improvement. Keep continuing this until we reach to a stable pi prime, stable policy. Right. So if you think about this, what is happening over here is for every iteration, I'm making use of the previous iteration's value function. Does it make sense? Right. So until I go over all of them and until it converges, I cannot do the policy improvement, which is this one. Now, problem with that is it is going to, it's not. So there is a theorem, I think sir did not prove, but mentioned in the lecture, that any version of generalized policy iteration actually converges and it is guaranteed to converge to optimal policy. And that leads to value iteration, which is this one. So what we are doing over here is, see this one. So this is step max of A. That means we are actually computing, taking all the actions and computing their. So this is estimate of the value function VS. Can you see this? VS of VK plus 1. Make sense? See, the only difference between this evaluation step here, this, and over this is this. Right? Here what we are doing is, in policy evaluation, we are particularly evaluating a policy and finding the correct value function for that. But our objective is to maximize value function, right? In order to find the optimal policy and optimal value function, our objective is to maximize. So instead of, first compute it thoroughly and then take the action, then go over here and take the action which actually increases the value function. What we are trying to do is, we right over here, after doing one step policy evaluation, we take the action which gives the maximum from that state.
So this is for a fixed policy, is it?
So value iteration does not depend on the, it's not conditioned on the policy.
Oh, how come?
See this one. So you start with, very much similar, in similar fashion of policy evaluation. You start with V0 for all the states to be 0.
But that V of anything, V sub of anything, now K here is iteration, I understand, but typically it is V sub pi of S, right? Like, so, or is it something like independent of policies, expected return overall? Is that something we are trying to do here?
Okay, so see, here we are not trying to find out the.
So V is defined in terms of policy.
Sorry?
V is defined in terms of policy, right?
No. So that's the interesting part of this. See, when we are making the transition, we are not taking samples from the this pi AS. We are only making the use of the transition probability and the reward distribution. So if I'm in a state, any state S, okay, there are 4 different actions available.
Sorry. Okay. So since it's max over A, what I'm trying to do is simply find which action is going to give me the maximum reward.
Correct.
Correct. And since it is a maximum of all actions,
right,
policy doesn't matter because I'm just enumerating over actions.
That is correct. Absolutely right.
But what if probability of A from given a set S is 0?
probability of given,
Like what if there is a policy which
Uh-huh.
says that one particular action should not be done at all?
okay, so there must be some other action which was available, right?
Right, but then we'll find the max of that also, even if that action can't actually be performed under policy by.
See, if that action cannot be performed, then we just ignore that.
Okay.
That's not a valid action in that state.
And no chance of it being the maximum action also?
If it is not allowed, then there is no possibility that it could give you optimal value function for that state.
Okay, okay. But okay, I think that I'm not too clear on. But what I'm getting here is that forget about the policy, just get everything that is for all actions at all times and find the maximum.
That's absolutely right. Yes.
Okay, okay. So we get basically a best set of actions.
So value iteration
for a given state, the maximum action. Okay.
Right.
So here's the maximum rewards over actions, and in the same thing previously we had. Can you go back to the earlier expression?
Yeah.
Was the maximum reward given a policy summed up over all actions?
Right. So here, see, first what we do is we sample from a policy, and instead of sampling from the policy, what I'm taking is I'm taking all possible actions, and whichever action gives me the best reward, I'm going to choose that.
Okay.
To estimate my value function, because at the end, this is what you're going to do. See, once you estimate the value function, then you choose the action which is going to give you the maximum reward.
Oh, I see. Okay, okay.
Right?
Now I understand.
And then you go back to this equation and then sample from that action as from that policy which was which you have updated, and from this, so this is going to give you the best arm.
And these two could be like completely different values.
Sorry?
Vk plus 1, which is let's say V of S, V star of S, which is computed through value iteration, is a very different number than what is computed through policy evaluation.
Actually, both of them, if you do both of them sufficiently large number of times, you're going to get optimal policy and optimal value function through both of them.
Oh, so the same thing, like, if the sample size is large enough, then we'll get closer to the true mean, that sort of thing.
Yeah, that's correct.
Okay. Cool.
So think about it like this. So now I'm going to come to the, so after sir actually explains these two things, so week 3 is policy iteration, week 4 sir starts with value iteration, and then he talks about why this method converges. So there are proofs available for this, but now let's look at this one, this particular approach. So what is this thing? I'm coming back to this equation again. So this is one step policy evaluation, if you think about it. So this and this are exactly same. Here, what you're doing is you're sampling from the, once from a state S, the probability of sampling an action A, and then you sum over all the actions. But still you compute this quantity, right? Yes. And here also you're computing the same quantity, but when you're actually making the update in value iteration, you're taking the action which gives you the maximum value instead of taking a mean of it, mean over the actions.
Right.
Right. So this quantity is computed in both the cases. Now,
right.
Since you are updating this value in value iteration, you are updating the value function of a state S just after doing it once. See here, how many times you would have updated? How many times you would have executed this step to compute the stable value function for state S? As long as it takes.
As long as theta requires.
This equation is satisfied, right?
Here
we are not doing that. Okay. As soon as I update it, as soon as I compute this value, I'm updating my value function for status.
Right.
Right. So if you think of it, this is actually one step policy evaluation.
Mm. Okay.
Okay.
I mean, the only troublesome thing here is that there is no policy at all over here. So
That's true.
why
That's
is it a good proxy for policy evaluation? But anyway, I mean,
right.
that's
Now,
it.
you're right. So now we come to okay. So first internalize this, and then I'll come to generalized policy evaluation.
Actually, I have to leave, and I think Deep also has dropped off.
I see. I see. So let me go through this quickly, and we can stop the session.
Okay.
So so now you know the equation for value iteration. So value iteration update rule does not involve policy. In order to get the policy, actually, once you have what should I say? Once you get the once you update the value function for all the states through policy iteration, then you can move on to policy improvement. Now there is a general theorem for which is called generalized policy iteration. It says that see, policy iteration, which we saw, is actually an extreme form of generalized policy iteration, where we don't move on to policy improvement until we have somehow somewhat converged the values of value function for all the states. On the other hand side, value iteration, what it does is, as soon as it gets as soon as it computes one step value function, it updates its value function, and it also computes and then it performs the greedy policy improvement.
Okay.
So, right. So here you can see that there could be many number of steps before you actually move on to policy improvement.
Right.
And in policy value iteration, you are seeing that as soon as you update your value function, you go to your policy improvement.
Right.
So these are two extreme forms of generalized policy iteration, and there are proofs which suggest that any you can you can take any granularity between policy improvement and policy evaluation, and if you do this enough number of times, sufficiently large number of times, you're guaranteed to converge to optimal policy and optimal value function.
Okay. Either way, even if those two things are extremes, they will eventually find the more or less similar results, is it?
That is true. That is true.
Is it possible to have completely different policies, both of which are equally optimal?
Yeah, there are. It is possible to have multiple optimal policy.
Right. Okay. But whatever, I mean, whichever extreme you come from, you will find one optimal policy.
That is true.
At least one.
Yes.
Okay.
So now this is generalized policy iteration, which gives you a convenient framework. So the later methods which we study, Monte Carlo methods and temporal difference methods, both of them are some form of generalized policy iteration, and hence guaranteed to converge to optimal policy given they are executed sufficiently large number of times for each step. So that is after generalized policy iteration. So it talks about Monte Carlo methods, which is a method with
simulations and numerical sampling and all, right?
Right. So no bootstrapping. So most important point about Monte Carlo method is no bootstrapping. And second very important part is actually it's assumed that you can sample trajectories from your environment. And very convenient assumption from Monte Carlo methods is knowledge of the environment not either required or not known.
I see. And okay, I guess this is based completely on sampling and stuff. That is why exhaustive knowledge is not required, is it?
That's true. That's true. So the reason for Monte Carlo methods to be very, very practical and usable. This. So first is if the system is very complex, we don't know the transition probabilities, which is this one. Right? This is not known at all. Or even if it is known, either it is simplified or incorrect.
Right.
In such cases, your policy iteration methods can lead to incorrect value functions.
Oh, right. Like, so it's like if the initial assumption is wrong or something, or if my probability transition is in a diagram or something, if that graph is incorrect, then in the beginning itself, it will go off on the wrong track.
Exactly.
Okay.
And
but this still means that I can come back to a good policy, except that it might take time.
Sorry.
So that since we already have some guarantees about this, right? So even if my initial assumptions are a bit wrong, I can still come back to an optimal. But no, if my initial assumptions about my transition probabilities itself is wrong, then there is no way I can fix that.
Yeah.
Okay.
Reaching optimal policy and value.
Oh, I see. So okay. So what you're saying is in Monte Carlo that P of transition probabilities are not needed to be accurately measured at all.
Absolutely right. That's the point. So
that sounds very strange.
Sorry. It doesn't have to be known, or if it is incorrect, we don't rely on it basically.
Oh, okay. So we give up transition probabilities entirely.
Yes.
Wow. Okay.
So what is the overall objective of our reinforcement learning paradigm is learning optimal value function and optimal policy. Is that correct?
Right. Like, because if I see the importance of it, because anyway, every agent is not going to be having pre-built information of what my transition probabilities are. That also will have to be learned, right?
That is correct. So let's say we generate a trajectory like S0, A1, I get R1, R1, or then S1. I end up in S1. When I take A2, then I get R2. And let's say for a second that I reach S3, or which is the terminal state. Okay, so I start with the initial state and just start generating trajectories, and that's all.
Understood.
And what I do next is, what is my goal? To compute the value function. So what I do is I start to do this. That's all. And how would I compute this one? It will be like R_1 plus gamma R_2, and that's all. So if the length of the trajectory is longer, we are going to get actually longer equation for computing the value function of this particular status.
Got it. And anyway, it goes down. If some particular point in the trajectory is very far, the reward is going to be correspondingly smaller for me. So anyway, my initial state is the most sensitive one, so I can afford to wait. And that's what I'm taking away from this.
I can afford to wait. You are right that
from the Monte Carlo perspective, I can afford to wait and learn a particular R later. Might not be very accurate about it right now.
Sorry, I didn't get that point.
So this trajectory, if it is very long, then anyway I cannot enumerate it properly at time 0.
Well,
right?
as
Because
long as it
will still take iteration, massive amount of iteration, right? Or recursion.
Yeah, we can get a massive amount of iterations as well as recursion also. So that leads to another very interesting thing, which is actually, okay, let me show that one. So let's say somehow somebody gets back to S0 again. So you make a transition and now you take action with 3. Something like this.
Hmm.
So what happened is in this trajectory, you are seeing S0 twice.
Okay. Hmm.
Okay, so in this case, now you have a choice with so if we look at only this thing, okay, S3 and R3 also.
Hmm.
And here also I will change it. Plus gamma square underscore 3.
R3. Hmm.
Assuming that we are starting from
S0.
0, right? So we are starting from S0, we are doing this. Another way to look at is, so see, if we assume that the trajectory is starting from here, you know, then the reward is R3 only.
Right.
Right.
I'm sorry, Swarnim, I really have a hard stop at 8 o'clock. I'll see you next week then. I'll watch the recording once and I'll have some questions. I'll post them on Discourse.
Sure.
Sorry about that.
No issues. Have a good night.
Thanks a lot. Bye.
Bye bye.